Hello everybody, welcome to Chapter 6.1 Part 1, Introduction to Radicals. Radical parts. So here is what a radical would look like. Here would be the index. If you don't see a number here, you just assume that it's a square or 2. Here is the radical sign, and inside the radical sign is what's called the radicand. If x is a non-negative real number, then the expression square root of x is called the positive square root of x and is the non-negative number where the square root of x, when it's squared, gives us back x. So, for example, the rule is the square root of a, and if a squared is inside the radical sign, a squared square root is equal to a if a is greater than or equal to 0. The negative square root of x, negative square root x, is defined in a similar manner. Notice how the negative is outside the radical sign. Example number 1. What is the square root of 64? So let us go over to the whiteboard and discuss what this means.
So example number 1 asks us to find the square root of 64. Well, we can look at 64 and we know that 8 times 8 is equal to 64 because that's what we want to square. Want to find the square and then to find the square root. I'll show you that in a minute. And also negative 8 times negative 8 gives us positive 64. But the thing is we don't look at this one. And the reason is because it can, by definition, it has to be non-negative. So we forget about this one, and we're just going to look at this one. So it turns out that 8 times 8, so if we do the square root of 64, that's equal to the square root of 8 times 8. And because this is done twice, we end up with 8 as our final answer. So this, by squaring that inside, like I said earlier, we could get back. So by definition, if we go back to the square root of a squared is equal to a times a, and that will give us a. So that would be our definition and what we are using here.
Returning to the PowerPoint, we found that the positive square root of 64 is 8 because 8 is the positive number with the property 8 squared is equal to 64. The negative square root of 64 is negative 8. Since negative 8 is negative number whose number is 64, we can summarize both of these facts by saying square root of 64 is equal to 8 and the negative outside of the radical sign, square root of 64, is equal to negative 8. Note, by definition, the square root of x squared represents a number which is non-negative. If x is negative, we must use absolute value symbols to ensure that the square root of x squared is non-negative. We write the square root of x squared is equal to bar x bar. This rule applies to any radical expression that has an index that is an even natural number. Hence, the square root of x squared is equal to the absolute value of x.
Now, the thing that you really need to know for this sort of stuff is you really have to know your root table. And if you look at your PowerPoint or your workbook, you'll see there's a list of roots that you need to know. You probably don't need to know the fourth roots for the certification exam. You certainly need to know the square roots up through about 13. And your cubed roots you should really know also up to about 125. So it's really important that you memorize those square and cubed roots that I listed there.
Radical rules. The main rules used to simplify radicals are the product rule for radicals. So if we have something to the nth root, a times b, we can break it up into two parts. We can break it up into the nth root a times the nth root b. For the quotient rule for radicals, if we have a over b, all in a radical sign, we can break that up into the nth root of a over the nth root of b. Observation. When dealing with negative numbers and radicals, the only restriction concerns negative numbers under even roots. We can have negative signs in front of radicals and negative numbers under odd roots and still obtain real numbers. Otherwise, we have to use imaginary numbers. We will learn more about imaginary numbers later in this course. Examples 2 to 4. Simplify each expression if possible. In 2, we're asked to find the cubed root of negative 8. So let us go over to the whiteboard and work this one out.
All right, now let's look at example number 2. And example number 2 is about a cubed root. So our index is 3. We're actually showing an index. So, and then we have a negative number underneath here, negative 8. And you'll say, but Professor, didn't you say we can't have a negative radicand? Well, in this case, that really is only for square roots. When we have odd number of roots, yes, we can have a negative sign. And the reason we can have a negative sign is we can look at underneath the rad. We're going to break that up into all the same 2 times negative 2 times negative 2. And it turns out that negative 2 times negative 2 is positive 4, and positive 4 times negative 2 will give us back our original negative 8. So that actually works fine. So it turns out, so this will be really equal to the cubed root of negative 2 cubed, and that will give us, so negative 2 cubed, so that will give us a final answer of negative 2. So if your index is odd, then you can have a negative sign underneath the radical. But if your index is even, like a square root or a fourth root, then you cannot, and that will indicate to you that we're dealing with imaginary numbers, which we will talk about later on.
Reviewing what we just did on the whiteboard, we found that negative 2 is the answer because negative 2 cubed is equal to negative 8. In example number 3, we're asked to find the square root of negative 4. So let us go over to the whiteboard and see what this one is.
That's the square root of negative 4. And you see, if we don't see a number there, we just assume it's the square root. So that means if we break it down into negative 2 times negative 2, what happens is we get a positive 4, and we try to bring it back again, a positive 4. This and this are not equal. So negative 4, positive 4 are not equal, so we cannot use that. And that's an example why we cannot have an even number, an even index with a negative number underneath our radical sign.
Reviewing what we learned on the whiteboard, we found it is not a real number since there's no real number whose square is negative 4. In example number 4, we have negative square root of 25. So let us go over to the whiteboard and work this one out.
But it's okay to have the negative sign outside the radical sign. If we have an even index, that's okay, because it turns out is equal to, and that would be -5, because we just end up taking the square root of this, putting the negative sign because it's outside of all of this, and we get a final answer of -5 this is just the regular square root, and then the negative sign is outside the radical sign. So that's the difference between when the negative sign is on the inside and when the negative sign is on the outside.
So let us review what we just did on the whiteboard. We found -5 is the negative root of 25. Examples 5 and 6. Assume all variables represent non-negative numbers and simplify each expression as much as possible. So here we're actually doing things with variables. So let us go to the whiteboard and work this one out.
Since we're going to be using and looking at things in algebra, that means we're going to be looking at things with variables. So in example number 5, we have the square root of 25, a to the 4th, b to the 6th. So what I'm going to do is I'm going to do a little bit of bookkeeping using my product rule first. So I'm going to break down, I'm going to do my square root of 25 first, and I'm going to break down all my a's, a times a times a times a, because this little 4 tells me how many times I have to repeat my a, and then here I'm going to repeat my b times b times b times b times b times b 6 times. So then what I'm going to do, well, we know from the last problem that the square root of 25 is 5. So we can just pull that out. Now, because this is a square root, that means we have to double these to take it out. So that means we're going to have an a from here, an a from here, and similarly, we're going to have a b from here, a b from here, and a b from here. So that means that our final answer, and I'm just going to, that our final answer will be equal to 5a, and since there's 2 a's, I'm going to put a squared, and 1, 2, 3, since there's 3 b's, I'm going to put b cubed.
So let us review what we just did on the whiteboard. We looked at all the perfect squares and broke them into their parts, the square root of 25, and we put the a's under another radical sign, we put the b's under another radical sign, and we broke them up into their perfect squares, and we found that we had 5a squared b cubed. Example number 6, we're asked to find the cubed root of x to the 6th, y to the 12th. So let's go over to the whiteboard and work this one out.
In number 6, we're going to look at a situation where we have a cubed root because we have a 3 inside the little radical sign here. And we have x to the 6th, y to the 12th. Well, now I'm going to break them down again like I did before. So we're going to do x, 2, 3, 4, 5, 6. And then we're going to do y times y to the 12th, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, just barely fitted. So now, because this is a 3, instead of gathering them up in groups of 2, we're going to gather them up in groups of 3. So now we can take the x out of the radical sign. And we can take another x out of the radical sign. And similarly for the y, 3, 3, 3, 3. So we have a y, a y, a y, a y. And that means, so here we have two x's. So that will give us x squared. And we have x cubed, sorry about, x squared, sorry. That'll give us x squared, that's correct. And then y, 1, 2, 3, 4, and then we have y to the 4th. And that's our final answer.
Let us review what we just did on the whiteboard. We looked for all the perfect cubes. So that means we put underneath the cube sign x cubed to represent x to the 6th, because if we add 3 plus 3, we get 6. And then underneath the next cubed sign, we put the y cubes. We have y cubed, y cubed, y cubed, and y cubed. So 3 plus 3 plus 3 plus 3 will give us 12. And then we take out each cube and we end up with x times y times y times y times y, and we end up with x squared y to the 4th. Simplifying and combining radical expressions procedure. 1. List all the possible pairs of factors for the radicand. 2. Choose the pair containing the largest factor, which is a perfect root. Example, square, cube, etc. Express the radicand as the product of two radicands, one containing the perfect root, square root, cube root, etc., and the other containing the remaining factor. If the original radicand contains a variable raised to a power, the power must be multiple of the index to be a perfect root. For example, it must be a multiple of 2 to be a perfect square, a multiple of 3 to be a perfect cube, etc. You will have to split up this exponent most of the time. Evaluate the radicand containing the perfect root and leave the other radicand alone. Use the rules used to simplify radicals. Remember, we went over the product rule earlier in this lesson and the quotient rule. Example number 7, simplify the square root of 50. So let us go over to the whiteboard and work this one out.
So we're going to simplify the square root of 50. Now, in order to simplify, you want to look at 50 and see if there's any perfect squares in there. Now, perfect squares means things that we can take the square root of. So what we can do, we can break this into 2 times 25. And we know that 25 is a perfect square. So what we're going to do, and I'll erase these rules, I'll just keep the product rule up there. So what we're going to do, and this is a square root, notice nothing, no number in there. We're going to break it based on the product rule, square root of 2, square root of 25. Now we know that the square root of 25 is 5. And by convention, we put our regular number outside the one that's next to the radical sign. So instead of writing 2, square root of 2 with 25 at the end. And the reason I do this is because if you make this too long or you don't cut it off, you don't know whether or not the 5 is inside or outside the radical sign. So this way it's very clear that we've already taken the square root of 5 and that the 2 remains in the radical sign.
Reviewing what we just did on the whiteboard, we found the largest perfect square that divides 50 is 25. We write 25 times 2. So 50 is equal to the square root of 25 times 2. and we take the 25 out of the radical sign using our product rule, and we end up with 5 square root of 2 as our final answer. In number 8, we're asked to simplify the following. The square root of 25, a squared, b to the 20. In this one, everything is a perfect square. That is, a factor of the radicand is 5a b to the 10th. In number 9, we're asked to simplify the following. The square root of 48, x to the 4th, y to the 3rd. So let us go over to the whiteboard and work this one out.
Now let's look at an example where everything is not a perfect square. And you may ask, well, what do we do about that? Well, that's what we're going to do when we see example number 9. And they ask us to simplify 48 x to the 4th y cubed. So we're going to do what we've done before. So I'm going to do 48 x squared. That will give us the 4th. And then the y, I only have one that's squared, and then the y that's left over to give us y cubed. So 48, it turns out, is 16 times 3. So we have the perfect square 16, which is 4, and then the square root of 3 left over. Here we can take 2 of these out of the radical sign and get 2x, so we can get x squared. And here we can take one of them out of the radical sign because of the square, but the other one is left inside the radical sign. So now what we want to do, so that means that this is going to be y. I'll just rewrite it for clarity. So this we're going to have that. Now what we're going to do is rewrite it where all the ones outside of the radical sign, usually the number is first, x squared y, and then underneath we put the radical sign, and what's underneath the radical sign is 3y. Let's get that squared a little bit closer so it can be seen. Okay, so here you see it, so that means that our final answer would be 4x squared y, radical or squared of 3y.
Reviewing what I just did on the whiteboard, the largest perfect square that is a factor of the radicand is 16x to the 4th y squared. So here's the calculation that we did. So we looked for the hidden perfect squares and put the hidden perfect squares and then everything that was left over. And then 16, the square root of that is 4. X to the 4th square root is x squared, y squared is y, and then the square root of 3y is what was left over, so that remains in the radical sign. In example number 10, we're asked to write the square root of 12, x to the 7th, y to the 6th in simplified form. So let us go over to the whiteboard and work this one out.
So let's look at example number 10. And that's going to be 12 x to the 7, y to the 6. Well, 12 is not a perfect square, but we can break it down into 4 times 3. 4 times 3. And 4 is a perfect square, even though 3 is not, so that would be 2 square root of 3. The next part, 7, well, we can write that as x squared x squared, x squared. So that means we have 6, and then one left over x. So we can take out the ones that are perfect, that are squares, which would be our variable perfect squares, and write those as x, 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 and then square root of x, which we can finally write as x cubed square root of x. And then the last one, y squared, y squared, y squared. So that would give me y to the 6, and I'm writing them so I can pull them out as perfect squares, and that means I get y, 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 and that will give us y cubed. So again, if I rewrite this with my with the things that are not under the radical sign, I would write that as 2 x cubed y cubed, and then I put my radical sign stuff, and I have 3x underneath the radical sign that was left over.
Reviewing what we just did on the whiteboard in number 10, we put everything in terms of perfect squares, or as much as we could put in terms of perfect squares. We took the perfect squares and put them in their own radical sign, and then put the leftovers in the other radical sign. And then we took out the perfect squares and then left everything else in the radical sign, and that became our final answer. In number 11, we're asked to find the cubed root of 54a to the 6b squared c to the 4th. In 11, we're asked to break down everything into perfect cubes. So what we want to do is we want to make sure that we put everything in terms of cubes. 3 to the 3rd power is 27. We have a to the 6th, which would be a to the 3rd power, a to the 3rd power, and then c to the 3rd power, and we have left over 2b squared c. So we put all the cubes under one radical or cubed root, and we end up with the 27a to the 6th, c to the 3rd, and then we separate out 27 cubed is 3, a to the 6th is a squared, c to the 3rd is just c. And then the leftovers are the cubed root of 2b squared c. Notice that b squared can't come out of a cubed root. So everything here remains within the cubed root because we cannot separate them out, and this becomes our final answer. In example number 12, we're asked to find the square root of 25a to the 4th b to the 9th. So let us go over to the whiteboard and see how to work this one out.
25a to the 4th, b to the 9th. And we do exactly like what we've done before. 25, break it up into its 2, because remember, if there's nothing here, we assume it's a square root. So we want to see how many squares we can get out of that. There, and then b. So 2, 4, 6, 8, 9. And now, since 25 is a perfect square, it is 5. We have 2 perfect squares in here, so it's a times a. And here, again, we have 1, 2, 3, 4. b, 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 square root of b. And now we end up with, putting it all together, 5a squared, b to the 4th, square root of b.
Reviewing what we did on the whiteboard, we separated out our perfect squares, and we ended up, after we simplified our perfect squares, 5a squared b to the 4th square root of b. Thank you very much. I hope you enjoyed this video. Be well, take care, and goodbye for now.